Okay, so I just thought this was funny. Anyway. All right, let's go to the next one. Get out of here, you guys. All right, so wind and solar have scaled up faster than any other sources of electricity in history. This is kind of a remarkable thing showing how long it took to go from basically zero to, well, basically 100 terawatt hours to 1,000 terawatt hours. And you can see for hydro, look at that, almost 40 years, coal, 32 years, gas, 28 years, nuclear, 12 years, wind, 12 years, solar, 8 years. That sort of captures just how fast these technologies are growing. All right, now windmills are nothing new. Stephen, you may have something to say about this, but the Persians are said to be the inventors of the first windmill sometime in the first millennium AD. And many think that the design spread to Europe via the Crusades, but we really don't know. But it was the Persians used wind energy to crush grain, and then in the 1800s, one of the things that really opened up the West, especially the Great Plains, was the invention of the Halliday windmill, which you see everywhere out in the countryside. And then the first offshore wind farms began operation in the 1900s. I wonder if that shouldn't be onshore. And then in the 2000s, there's going to be, just incredible millions of homes powered by wind energy. And over on the right, we see the famous Dutch windmills. And that juxtaposition of the Persian design with a vertical shaft, vertical axis of rotation, and it's circulating around that, and this horizontal one that the Dutch modified. Those are the sort of two technological philosophies behind windmills. We'll see that it's been the horizontal axis that has taken over. Okay, so it's 1854. Daniel Halliday patented the wind pumping windmill, and that changed everything. Here's his original patent and how it was modified. They pretty much look the same everywhere, and they've been used for pumping groundwater ever since. Just amazing how they changed the West. Yes, Clint.
I just want to point out that the new ones, or the newer ones on the right, which are quite common, look much less scary than the one on the left.
All right. So, as I said, there's two main types of wind turbines today. There's the horizontal wind axis wind turbines, or the HOT, and then there's the vertical axis wind turbines, which is the VOT. And we'll talk about these. I mean, we're going to see this different views of the thing on the left over and over again. And we won't really talk very much about the one on the right. One of the differences is that the HOT has to be pointed in the direction of the wind, and the VOT does not. But it's not hard to do that now. So your book shows these examples of VOTs, of a VOT in Quebec. And so currently the commercial development focuses on these HOTs for turbines that generate more than a megawatt of electricity, and we're going to explain why later. So this shows the growth. Average turbine hub height, rotor diameter, and nameplate capacity. So here's the capacity in these gray bars. They started off at less than 1 megawatt, and now you're up over 3.5 megawatts. Here's the hub height, which changed, the height of this thing to the ground from, what was that, 60 feet to over 100 feet. And then the rotor diameter, basically, that increasing from, what is that, like
That's
60 meters and over 140 meters.
Those things are giants.
Yeah, they are. Watch a 2-minute video.
We've all seen those creaky old windmills on farms, and although they may seem about as low-tech as you can get, those old windmills are the predecessors for new modern wind turbines that generate electricity. The same wind that used to pump water for cattle is now turning giant wind turbines to power cities and homes. Okay, have a look at this wind farm in the California desert. A hot desert next to tall mountains, an ideal place for a lot of wind. Here's another one on the windy prairies of Wyoming. Now, today's wind turbines are much more complicated machines than the old prairie windmills, but the principle is the same. Both capture the wind's energy. Okay, here's how it works. First, a wind turbine blade works sort of like an airplane wing. Blowing air passes around both sides of the blade. The shape of the blade causes the air pressure to be uneven, higher on one side of the blade and lower on the other. And that's what makes it spin. The uneven pressure causes the blades to spin around the center of the turbine. On the top, there's a weather vane that's connected to a computer to keep the turbine turned into the wind so it captures the most energy. Now, the blades are attached to a shaft, which only turns about 18 revolutions a minute. And that's not nearly fast enough to generate electricity by itself. So, the rotor shaft spins a series of gears that increase the rotation up to about 1,800 revolutions per minute. And at that speed, the generator can begin to produce electricity. So, why are wind turbines so tall? Well, the higher up you go, the windier it is. More wind naturally means more electricity. Larger turbines can also capture wind energy more efficiently. The blades can sweep a circle in the sky with a diameter longer than a football field. Now, what's really cool is that even a small wind farm like this one in Wyoming can generate enough electricity to power more than 9,000 homes. And larger farms can provide much more clean energy for our homes and businesses. And it's not just on land that turbines can capture the wind. Our oceans and the Great Lakes provide a reliable and consistent source of wind that we can capture and turn into electricity. The Energy Department is supporting innovative offshore wind projects that will help build some of the first offshore wind turbines in U.S. waters. As the wind energy industry continues to grow, offshore development has the potential to significantly boost domestic renewable energy production, especially in coastal areas. With more than 50% of the U.S. population living within 50 miles of a coastline, capturing wind off America's shores has the potential to provide energy to countless homes and businesses. Wind energy, on land or offshore, a reliable and renewable clean energy source, helping move America toward energy independence.
All right. So here's the setup. So we've got a schematic wind turbine here. We've talked about this, and then this is the generator, and that sends the electricity down to a transformer that jacks it up to the voltage needed to transmit it long distances, and then it's just fed into the grid, right? So U.S. onshore wind capacity has almost tripled in 9 years, and in Texas, it's almost quadrupled. So these United States going from this is capacity, right? That doesn't mean what it's actually generating, because we'll see that the wind is not always generating the electricity that the wind turbine is capable of. But this is the rated capacity. So it's some fraction of this is actually being generated. So that's like 60 or 65 gigawatts, and in 2023, 150. So that's almost tripled. And in Texas, we went from about, what is that, about 14,000 to over 40,000 in the same time period. So it's almost quadruple. So Texas, being the green left loving state that it is, has completely embraced wind energy. Well, that's not what happened, is it? All right, so let's look at the wind energy by nation. So these are the onshore and offshore installations. So China leads the world in offshore and onshore installations by far. The United States is second, at least on onshore. UK is second in offshore, and the United States really doesn't show up much in offshore. So we're definitely here because we've got lots of land. Yes, Clint.
This would be a good place to put in I'm interested in where the wind energy is being generated in China. Like, for example, Texas is uniquely adapted, the western part of the state, for wind energy, whereas some of the mountain states aren't so much, even though there's high wind in there. And of course, China is quite varied geographically.
Well, that sounds like an excellent idea for a student project. All right. So as I said, Texas is by far the leading U.S. state in terms of wind energy because it's such a leftist, tree hugging state. You know, it's far ahead of all of those other states. I'm being funny. I'm being funny. So I mean, it just stands out,
I'm
right?
laughing, I'm laughing.
Anyway, this is what's controlling it is the average annual wind speed at 80 meters above the ground. And so you can see this zone here. These, these zones, these colors are higher wind speeds, and we'll see why it's wind speed is so important. So I mean, Texas, if we look at this, most people in Texas live over here, but the wind is way high over here where there's not so many people. So that's why.
And
You've
you'll
got
notice this looks
lots of
this
room
looks a
for
lot like a geologic map.
it does.
It,
It's a
it,
wind
it's
energy map.
Yeah,
It's
it's
basically,
I mean, it tracks right onto a geology map of the Great Plains and the
yeah,
mountain, and you see the mountain belts and everything.
yeah, and the mountain belts in general are not terribly high wind, average annual average wind speeds. And we'll see what's needed is not high winds. It is we'll see why the having a continuous wind is so important. So anyway, 7 of the top 10 wind energy producing states are in the wind power corridor: Texas, Oklahoma, up in here. They're all quite taking advantage of that energy source. So wind is number 2 and a rapidly growing part of the ERCOT energy mix. So we've talked about this before. So this is natural gas. That's both kinds. And that's 42% of the electricity is generated by natural gas. Wind is 24% and growing. Coal is 13% and shrinking. Solar is 12% and growing. Nuclear. So, it's quite amazing how much of Texas's electricity is generated by renewable sources or non-CO2 generating sources. All right. So now we get into the book goes into noise and visual impact because politicians will say things like, "Oh, wind turbines are a health hazard and they're unsightly, et cetera, et cetera." And this is the book talks about this. Wind turbines emit a weak noise that's mainly generated by the movement of the blades through the air. This produces a swishing sound, or maybe for UTD it would be a whooshing sound. And there's also a noise from the turbine machinery, and machine noises can be annoying to those nearby. But generally speaking, these wind turbines are not near population centers. So the latest wind turbines are much quieter than those of 50 years ago, and the noise from the gears and the generator have been reduced. That's easier to reduce than the wind of the turbine, the noise that the turbines make. So anyway, the noise from a modern wind turbine is like that of a tractor. So a typical 1980s turbine generating 100 kilowatts, which is lower than today, and a 1990s turbine generating 500 kilowatts, both emit about 100 decibels. So here's the decibel range. So loudness levels of common noises. So a quiet bedroom is about 30 decibels. A jet plane takeoff or amplified rock music 4 to 6 feet away, car stereo, band practice is up at 120. So this generates about 100 decibels. And that is Once you get farther away, nobody's standing right there near where the blades are. Once you get 750 or 1,000 feet away, it's only 35 to 45 decibels. And then another thing that some people might be annoyed by is the shadow flickering from the moving blades can be annoying, but that's your book's treatment of the noise and visual impact problem. So there is an entry called wind turbine syndrome in the Wikipedia, and these are terms for the alleged adverse effect, human health effects related to the proximity of wind turbines. Proponents claim these include congenital abnormalities, cancer, and death. The distribution of recorded events, however, correlates with media coverage of wind farm syndrome itself and not with the presence or absence of wind farms. Neither term is recognized by any international disease classification, nor do they, it's characterized as pseudoscience. So, we've talked about the levelized cost of energy a lot, and what you can see is that wind, onshore wind, solar, and natural gas are kind of, if you're in the business of making energy for money, that's where you're going to go. But Trump lies about the wind energy. Oh, I should mention that the UT system has adopted is pushing the universities, including UTD, to develop standards for dealing with controversial topics in class. And I think one of the things it's going to be is if there's actually facts, then you can talk about it. And if there are no facts, then or if it's not pertinent to the course, you shouldn't talk about it. So I think this little video is pertinent to this discussion.
On building infrastructure that's no good, but environmentally friendly, on doing windmills all over the place that are by the way, the most expensive energy in the world. You cannot get more expensive.
Now remember, windmills are not coming down. More windmills are being built. They're not even, I don't even know why I say windmills. More wind farms are being built than the number that are being decommissioned. I think what he's referring to is that the blades ultimately need replacement. It's not the most expensive form of energy. In fact, it's quite efficient. It has high initial costs to build the wind farms, but Trump doesn't care and his followers don't care.
On building.
All right. So let's go to the life cycle greenhouse gas emissions, land and water use. The next topic in your book. So there's a few tens of grams of CO2 emitted per kilowatt hour for wind generated electricity. That's, the actual generation, the rotating turbine doesn't put out any CO2, but you have to consider what it costs to create all of the components that go into a wind station and factor that out, over the lifetime of the turbine itself. But so if you do that, it's a few tens of grams of CO2 emitted per kilowatt hour versus about 1,000 grams per kilowatt hour for coal generated electricity. So it's ridiculous to talk about them as being anything other than environmentally friendly. The wind turbines use very little water, but there is a reality that constructing a wind farm can cause erosion and disrupt wildlife habitat. And you see this all the time. Yes, Clint.
Yeah, I was going to say one of the things about because they move and are somewhat spectacular looking, people think of them as being exceptionally dangerous to, for example, migrating birds. However, tall buildings of any sort and power lines are dangerous to migrating birds. And
we're going to get into that. We're going to get into
I was going to say all the birds aren't dead yet.
Yeah. All right. Well, so you see this, right? Yeah, it shows up all over the place. And yeah, disposing obsolete blades can be a problem. There's no question about it. All right. This is Clint's favorite topic, bird and maybe less favorite, bat fatalities. So This is out of your book, the most common causes of bird fatalities. And building windows cause 59% of the deaths. Power lines, 14%. Cats, Clint, 11%. Automobiles, sure. Pesticides, yeah. Communication towers, yeah. Wind turbines, not so much. And the book says, if we used radar to monitor migratory bird flocks, then this could reduce bird fatalities even more. And we can use radar for that purpose. There are higher rates of fatalities due to wind turbines for bats than for birds. Birds can see the turbines and avoid them. Bats, they use a kind of a sonar to navigate. So they can be killed by what they call a barotrauma, which leads to internal hemorrhaging due to rapid changes in air pressure around the rotating turbine blades. So, if people were opposed to wind turbines because of their love of the bats, that would be a different matter than their love of the birds, because it's just nonsense that wind turbines are killing birds. Okay, so here we've got the 10 countries with the most installed wind power capacity. China, followed by the United States at about about a third of China's, and then Germany, India, and on down. So I do want to show you this video.
Trump comes out today. Did you hear what he said about windmills in China?
No more.
Yeah, go ahead and play this clip, Rob, about Trump talking about windmills in China. I just sent it to you. Trump comes out and says the only person winning of buying windmill is China. And he calls them stupid people who buy windmills.
They make the components.
Yeah, watch this here. Go ahead, Rob.
Windmills all over Europe. There are windmills all over the place, and they are losers. One thing is that the more windmills a country has, the more money that country loses, and the worse that country is doing. China makes almost all of the windmills. And yet I haven't been able to find any wind farms in China. Did you ever think of that? It's a good way of looking at it. They're smart. China's very smart. They make them, they sell them for a fortune. They sell them to the stupid people that buy them.
Yeah. So anyway, Trump will every once in a while talk about somebody that has problems with him as suffering from Trump derangement syndrome. And I would have to say, well, if that's a real thing, then I think there's a wind energy derangement syndrome as well. And he clearly has a pretty good case of it. Okay. Now we get to the book goes into power and energy of wind. This is now we're talking a little bit of physics. But it's really interesting. So power is just work over time, right? Which is just energy over time. And we quantify it with Newton meters per second or joules per second, which is the same thing. And that's the joule per second is a watt. So wind towers are rated in terms of power capacity. So the large ones have power ratings of 1 to 5 megawatts, probably bigger now. So the energy is equal to Newton per meter, right? Energy is Newton meters, not per meter, and that's a joule. So energy is how much work can be done by a force, Newton meters. So wind energy is kinetic energy. It's moving. So if you look here, here's the equation for kinetic energy. Kinetic energy is 1/2 times the mass times u, which is velocity. So that's the mass of the air, and that's the velocity in meters per second. So you have to check the units. Kilograms, meters per second squared, kilogram meter squared, blah, 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 blah. Yes, that's joules. All right, imagine a horizontal cylinder of moving air of area A swept out by wind turbine blades. So this is the amount of air that's moving through the blades in a second. So that's got a mass, right? That mass is equal to the density of the air times the volume. This is the volume of the cylinder. So that's equal to the density of the air times the area times the length, right? And that length, the amount of material that's going to go through wind blades, is basically the velocity times time. So the mass is equal to density of air times the area of the blade sweep out times the velocity times time. Okay, pretty simple equation. It's just the kinetic energy that wind energy holds. Okay, so this is kind of showing you what's going on in the engineering of these towers from 1995. We're looking at 60-meter tile, with what is that? Maybe a 40-meter radius. And now we're looking at things that are over 150 meters tall, 200 meters. This is the upcoming design. So basically in 2022, the average rated power of a new wind turbine in Texas was about 3 megawatts. So that was a significant increase just from the year before. So the kinetic energy is, we've already gone through that. Right? We've seen this before. Combining the equations and solving for power is equal to kinetic energy divided by time. So that's going to be 1/2 density area times the velocity cubed, right? So in order to get this area, that's just pi r squared, where r is the radius of the turbine. So the power scales with the square of the turbine and the cube of the wind velocity. Okay, this is very important. The power increases as the cube of the wind velocity and as the square of the blade length. You want strong, steady winds to maximize electricity. So the key point is that a wind turbine with 100-meter long blades generates 25 times as much electricity as a turbine with 20-meter blades. Okay, so that's one reason that you want to have these bigger radius things. And in order, obviously, for them to sweep, they need to be up above the ground, but they don't have to be that high. There must be something else that's going on to make the engineers want them to go higher. All right, so here we've got this wind energy for the United States, and here we've got this equation for the power that's available as a function. So think about the significance of 8-meter per second wind versus 4-meter per second wind from an economic point of view. Anybody have any ideas? Any thoughts? Anybody want to venture how much more power you would get if you doubled the mean wind speed?
8 times.
Okay, so that is doubling the wind speed. So the wind speed is here. So if you go 4 cubed is 48, right? And 8 cubed is 64 times, what's 8 is, what, 3,500 or something like that. It's amazing.
Double cubed 8 times.
Double cubed.
If you double the velocity and you cube it.
Well, let me just, yeah, let's just check our math. But it's an amazing difference in the amount of energy you get with relatively modest differences in wind velocity. So let's see. 4 times 4 times 4 equals 64. 8 times 8 times 8 equals 512. So it's almost 10 times. Not quite, but yeah. It's a huge difference. So if you're gonna invest in a wind turbine, you're gonna be looking at this place. You're not gonna be looking at northern Louisiana or even California. You know, California wind resources on land are trivial compared to the wind power corridor. All right. Now, power also increases a lot. I mean, we've already said it increases a lot with wind velocity and blade length. And the key reason that wind towers are growing taller is to reach faster and allow for longer blades. So here's out of Wikipedia, and I've added this new giant one, the Haliade, the 2023 one, 260-meter tower. So this is the average rated output for a wind tower from 1990 to 2016, and you can just see how it's going up. Right there's a 1990 tower with a 40-meter tower and a 24-meter diameter.
Beep, beep.
There's what's that?
I was going to say Texas A&M has the biggest research tower in Texas up at Canyon near Coladero.
How big is it?
Real big. It's at the end of my sedimentary basins video, I think.
Okay. So they're just getting taller and bigger, for those reasons. So the most powerful wind turbine in the world that I could find is the Mingyang Smart Energy 22 megawatt. That has a rated capacity of 22 megawatts and a rotor that's over 310 meters long. That's amazing. All right. So one of the problems with longer blades is that taller towers and longer blades, number one, they're more expensive, but they're also more vulnerable to gusting winds. And we do get gusting winds. And then you've got the transportation costs. I don't know if you spend much time out in West Texas, you're sure to see something like this. So, just imagine this contraption trying to make that turn, huh? It's just amazing. The longer the blade, the harder it's going to be to make those turns. All right. Now, let's talk a little bit more about, sort of how wind energy works. And the book talks in section 8.4 about the coefficient of performance. So this CP measures the percent of the wind power that can be extracted by a wind tower. So CP is the power in the wind. Power in the wind. It's actually the power in the wind turbine divided by the power of the wind. Okay, and we've already talked about the power in the wind by this kinetic energy equation. But in fact, the coefficient of performance for any wind tower is limited by what's called the Betz limit. And I'll bet that's on the midterm. So that's basically, the Betz limit is only 59% of the available wind in the available power in the wind. And you go, well, that's interesting. Why is that? Okay, so this is your book explains. If all the energy coming from wind movement through a turbine was extracted as useful energy, the wind speed behind the turbine would drop to zero. So if that happened, then no more fresh wind could come in. It would be blocked. So in order to keep the wind moving through the turbine, there has to be some wind movement, however small, on the other side with a wind speed greater than zero. So this Betz's limit basically addresses this quantitatively. I'm not going to derive it, but basically the geometry list limits any turbine efficiency to a maximum of 59.3%. So today, the most utility scale wind turbines achieve 75 to 80% of the Betz limit. So that's about 40% of the total wind energy can be extracted. Okay. And the book also explains, in addition, the coefficient of performance is a function of how fast the tips of the wind turbine blades rotate compared to the wind velocity. So the turbine tip speed ratio, which is this omega R, that's the rotational speed. So we talked about 18, the blades are moving at 18 rotations per minute. And then, so those in radians per minute. So just to remind you, a circle has about 6.3 radians in it. And then R is the rotor radius, and the wind velocity is down here in the denominator. All right, so this is basically showing the various turbine power coefficients. So up here is the Betz limit at 59%. So this is the ideal efficiency of a propeller type turbine, like a wind turbine, right? It's lower until you get up to, these turbine tip speed ratios on the order of 4 from that equation, right? So here we've got different kinds of rotors. There's a Savonius rotor. I don't really remember what that is. That's a American farm windmill, the Halliday type thing. These are Dutch multi-blade turbines. This is a modern vertical axis wind turbine. And this is a modern horizontal axis wind turbine. So you can extract more energy out of the wind using this technology than either of these others. So in general, the horizontal axis wind turbines can generate 10% more energy from the same wind as a vertical axis wind turbine. That's pretty much why modern wind turbines are all high horizontal axis wind turbines. Okay, then the book starts talking about the aerodynamics of wind turbine blades. So basically, it shows this. So here we're looking straight down the axis of the wind turbine, right? There's the hub, and here's the blade coming off of it. So there's the leading edge and the trailing edge of the blade. This is the blade root. So that's kind of the geometry of a single blade with the relationship to the axis. So the wind's blowing into the paper. So the rotational velocity is equal to that, the rotational, the number of radians per second times the radius. Now this is a cross section through the blade. So there's the trailing edge, there's the leading edge, and you see it looks like an airplane wing, right? It's flat on one side and it's curved on the other. The wind is coming from this direction. So there's two forces acting on the blade, the incoming wind velocity, right? U times W, right? That's the U sub W. Velocity, wind velocity, and then there's the rotational wind speed, which is that expression. So you notice that the side of the blade facing the wind is flat and the rear side is curved. Why is that? And that's got to do with aerodynamics, right? Aerodynamics we're comfortable with because it's basically how airplanes fly, but the same physics applies to the movement of wind turbines. So here's the blade cross section near the blade tip, right? We're going to talk about the cross section near the hub and near the tip of the blade. And you can see here's the wind coming in, and then it flows over the flatter part and it flows over the curved part. So these are the forces that are acting on it. there's a drag force, but the lift force is like this. So that's kind of the same lift force that's involved with an airplane wing. You could imagine that the airplane is flying this way, and it's basically generating its own wind as it flies through the air. So this physics is explained by Bernoulli's principle. So Bernoulli's principle basically states is that the increase in the speed of a fluid, including air, occurs simultaneously with a decrease in static pressure or a decrease in the fluid's potential energy. So this is P, static pressure. This is velocity. So this is some kind of a constant. So it's like, okay, I'm not sure what that's telling you, but so let's watch a video. This explains Bernoulli's principle.
Hi, my name's Jamila. I'm an explainer at the National Air and Space Museum's How Things Fly Gallery. And today I'm going to talk to you about lift. I'm standing in front of the Spirit of St. Louis airplane. It was flown in 1927 by Charles Lindbergh, and it was the first successful solo flight over the Atlantic Ocean. Now, how was this plane able to generate lift? How was it able to stay in the air? Now, I can explain that using this airfoil here. An airfoil is like a cutout or a cross-section of a wing. So if I were to take a wing and slice it into pieces like a loaf of bread, this would be one slice of the wing. Now, if we compare this airfoil to the Spirit of St. Louis, we'll notice they have very similar shapes. They have curved tops and flat bottoms. An airplane's wing will be shaped this way because of something called Bernoulli's principle. Daniel Bernoulli was a Swiss mathematician who studied the movement of fluids like air and water. And he realized that a faster moving fluid will have a lower pressure, while a slower moving fluid has a higher pressure. Now let's apply this to our airfoil or to a wing, so that when the plane starts flying and air hits the wing, you're going to get faster moving air on top. It's going to speed up because of the curve. At the bottom where it's flat, you're going to have a slower moving air. It's not going to be as fast as the air on top. That slower air is high air pressure, and the faster air is low air pressure. That high air pressure pushes up on the airfoil or up on the wing, and that's why something as heavy as an airplane can fly. Don't believe me? Well, I have an experiment we all can try at home with a single sheet of paper. If I were to place this paper beneath my lips and blow, would it go up or would it go down? Let's see what happens. We notice that the paper goes up. And the reason why is because of Bernoulli's principle. When I blew my fast air on top of the sheet of paper, it was a lower pressure than all of the air in the room, because the air in the room is slower than the air that I was blowing. So that high air pressure works from beneath and it pushes up on our sheet of paper. And the same thing is happening to an airplane's wing. And that's why something as heavy as an airplane, like the Spirit of St. Louis, is able to generate lift. Hi.
Okay, now, and that, she's talking about airplane wings, but it's the same thing applies to turbine blades. The instead of using that shape to lift a heavy object in the air, that pressure difference causes the blades to rotate. It's not the wind pushing the blades, it is the wind blowing around the blades that's causing the lift force that is causing the rotation. Does that make sense? I mean, when I first started teaching this course, I thought, oh, the wind was blowing the blades like when you have a pinwheel. You got one of those little pinwheels you give kids. You're actually pushing your air when you blow on, you're actually pushing the blades, but that's not the way to make maximum efficiency. This is the way to do it. Okay. It's kind of cool to learn Bernoulli's principle. It's like, I wasn't expecting to learn Bernoulli's principle in this course, but you really can't understand how wind energy works now unless you do it. So the point is that wind turbine efficiency depends on careful aerodynamic design. Okay. Any questions about that? Super cool. All right. Now, this is what the the blade looks like near the tip, right? So we're going to look at two sections here. Here's the section of the blade near the tip, looks like that. And then we're going to look at another one near the root, this is where the hub is. Okay? So this is designed to keep the blade rotating. It's not designed to get it to rotate, it's to keep it rotating. On the other hand, this is a very different orientation near the root. So instead of the wind, coming in like that, it's coming in at a higher angle. And so the lift is in a different direction, right? You see the difference?
So that's why
Between
they
the-
have that.
You
That's
see
why they
this
have that
lift is
twisted
more,
look.
almost more vertical. This lift is more forward. Go ahead, Clint.
I was gonna say that, so that's why they have that twisted look. I always noticed that, but never really thought about it.
No, it's you're right. I mean, that the book is really good in really walking you through what's going the physics of wind turbines, which are quite remarkable. So this geometry, this is designed to start the stationary blade moving, right? An airplane takes off because it just generates so much thrust, right? There's no thrust, there's no starting this thing except by the wind. So they had to engineer the blade so that it would start the blade spinning. And that's what that twist is for. All right. Now this gets us to the physics of wind, right? The wind is different. We've already seen that map of the United States that the wind in the high plains is optimal. The wind power corridor is this region. But the understanding the wind is, most of what we've been doing now is like, what's this got to do with earth science? But so now we can talk about winds, which is earth science.
This animation, we're going to look at global wind patterns and talk about the reasons why the air circulates the way it does, and also patterns of rising and sinking air and how that relates to precipitation. The engine that drives it all, I guess you could say, is the intense heating by the sun that occurs in the equator areas where the sun is shining at a very high angle of incidence. And this hot air near the equator, being less dense, rises upward. It rises upward and it moves toward the poles, and then it gradually sinks at about 30 degrees north and south latitude. So we create these big spinning circles of air that we call the Hadley cells. Now, near the equator where the air is rising, it loses its ability to hold moisture, and you get a band of high rainfall and low pressure because there's air leaving the equator. Where the air sinks in these belts at around 30 degrees north and south, you get high pressure sinking air, which creates areas of clear skies and desert climates. Now, as this air circulates and tries to flow back toward the equator along the surface of the Earth, or as some of it heads toward the North Pole or toward the South Pole, the Coriolis effect, the spin of the Earth, causes it to bend and turn, and it's going to create the two big wind belts that prevail on our Earth, 2 out of 3, the trade winds, northeast trade winds and southeast trade winds, and then the prevailing westerlies. Now, these winds curve in the way they do because of the Coriolis effect. The winds curve to the right of their path, north of the equator. They curve to the left of their path, south of the equator, and they end up flowing from east to west or from west to east. Now, the other big factor is what's happening at the poles. At the poles, the air is cold, and the cold air wants to sink. And as that cold polar air sinks, it heads toward the equator and it bumps into this air heading toward the pole here and toward the South Pole here. And it creates an area of rising air. And again, rising air produces high precipitation belts at about 60 degrees north and about 60 degrees south latitude. At the poles themselves, the precipitation is quite modest because the air is sinking, and that creates low precipitation.
All right. now your book gets into the atmospheric boundary layer. So boundary layers are interesting geological topics. We talk about boundary layers, between the mantle and the core, and between the crust and the between the lithosphere and the asthenosphere. But we don't really talk about the atmospheric boundary layer very much, but it's very important for understanding wind energy. So it's the lowest part of the atmosphere. And basically, it is a zone where the wind speed varies from zero right at the surface up to what you could call the free stream velocity above the atmospheric boundary layer. And there's a lot of turbulence in the atmospheric boundary layer, which negatively impacts wind turbine performance. And this turbulence is especially high near the surface. So in order to reach the maximum speeds and the minimize the turbulence, you want to build wind towers as tall as possible. And that's what's motivating these taller wind towers, is they're trying to get above the atmospheric boundary layer. Okay? And we'll talk more about what the atmospheric boundary layer is.
Let's look at the variation of the planetary boundary layer over the course of a typical day. We'll start midday when the sun is out and solar heating of the surface is causing buoyant air parcels to rise until the virtual potential temperature matches that of the overlying air. These air parcels have momentum and they overshoot the level of neutral buoyancy. In the process, they entrain air from the free troposphere. Clouds form in this layer. The rising air parcels collide with the air above them and rub against the air around them, producing a whole range of different eddy sizes and mixing. These large buoyant eddies cycle in tens of minutes, mixing the air. As the sun sets later in the day, there is less solar energy to power the convection that stirs the mixed layer, and the boundary layer collapses, leaving behind a residual layer that contains the mixed layer air that was left over. Emissions from the surface keep pouring into the boundary layer, but the boundary layer height is much lower. With less turbulence in the residual layer, the air can speed up. Faster moving air above the slower moving air in the boundary layer causes a shear to develop between the two air masses, and sporadically turbulence is generated when the shear breaks down, mixing air and increasing the boundary layer height. At sunrise, solar heating again begins to warm the surface, and the warm parcels rise up, entraining residual layer air, until eventually the mixed layer reaches its maximum height again.
Okay, here's a question for you. Learning that, what time
Let's look at
what time in a 24-hour day would you get the best performance out of a wind tower? Anybody?
Afternoon.
No, in the afternoon, the atmospheric boundary layer is well developed and tall. So
At
that
night?
atmospheric, yes, at night, because the atmospheric boundary layer collapses, and is closer to the surface, and then in the daytime, as it heats up, it rises again. So you have all of this turbulence, and wind towers don't like turbulence. We're going to talk about turbulence again. All right, so back to this map. Does everybody understand that one of the challenges is that wind energy is at a maximum at a time you don't really need the electricity. It'd be nice if the maximum time was in the afternoon, because then we would that's when our demand is high, right? And people are awake. All right, so the book then goes on to the distribution. Yes, Clint.
Just going to say, and this, keep that thought in mind as we later go into storage. But that's off-peak generation is something that is not a dead loss.
No, not if we have good storage, good battery storage. Yes, good point. So the wind resource, this is, we normally don't think about wind resources, but we need to, because that's really what the wind energy industry is based on, is understanding where it can get the maximum sustained wind energy. And that's why these maps are so useful. So here we got the map again. And the wind resource is just the mean wind speed and how many hours per year the wind blows at a given speed. And we'll see why that's important in a bit. So any wind farm developer, in order to build a viable economic plan, business plan, they need to be confident that the wind speeds at a given location are high and consistent from year to year. And this confidence in wind speeds and consistency is important for investors. Yeah, and we've talked about, if wind speeds are slightly lower, you get a lot less electricity. And the book talks about, if wind speed is 5% lower than predicted, that results in 14% less electricity and 14% less income. So it's a very important consideration. So why are the U.S. high plains so windy? We didn't see anything in either the videos that would help us understand why the wind power corridor is where it is. So I reached out to a professor at Texas Tech, who was pretty well known for his work in wind energy, and he responded to my email. I believe that for the South Plains, the key factors are the high frequency of clear skies and the elevation, particularly during the cool seasons. That promotes mixing down of the stronger winds aloft. So that's what he's had to say about why the wind corridor is where it is. All right. So now there's some other considerations that are useful to think about. So we've seen the wind power corridor over and over again, but the interesting thing is it's also a low population region, and wind farms are just much easier to put up in areas where there aren't very many people. Whatever, you're always going to have complaints about wind power from not only the President of the United States, but also local populations. Anytime the people can see an opportunity for a lawsuit or a settlement, they might take it. So you want to be away from people, because the proportion of the number of nuts per unit area is some constant times the population of that area. So low population are good. And also the reason this area is low population is because it's not really very good for the kinds of economic activities like farming. It's ranching. This is mostly ranching territory. So you can see that from the way that the United States uses its area. So this is the land use area map. So urban, obviously, there's Dallas, Fort Worth. Special use, cropland. You can see where the cropland is, right? In the Midwest and some of these regions. And then there's some forests. But pasture and range, that's pretty inefficient land use, all things considered. And this is a lot of pasture and range there. And really, these wind towers don't really bother cattle. The cattle, as long as there's grass on the ground, the cattle are pretty happy. All right, so here we're looking at the state of Texas. This is the annual average wind speed at 80 meters. So why 80 meters? Well, that was when this was done, and you can see this is done by NREL, now known as the National Rocky Laboratory. That was the average height of the wind towers at that time. So that's when these things were made. And so here we're looking at average wind speeds, meters per second. There's Dallas. So we average, somewhere between 6 and 6.5 meters per second wind, averaged out over the year. And then look up at Amarillo. That's up in 9, 8.5, 9. These purples are up here. So you can see where, oh, look at, that red one there in the northern Permian Basin. That's lower. So you're going to be, you're going to be interested in wind farms down here by San Angelo and Big Spring, Abilene, Lubbock, Amarillo. You can see why Texas Tech is interested in wind energy. So that's basically a map for where you want to put your wind farm. So as we said, Texas is leading the U.S. in wind energy, and this is I forget what year this is. It's the most recent one I can find. Sorry, I don't have the year on there, but it's just far and away Texas is leading the other states. And here is the location of the wind farms, the most recent one I could find. There's, mostly they're just following that map where the high wind speeds are, and avoiding the eastern part of the state because it's, no investor in their right mind would put them there. Land is cheap over here and the wind speeds are high. All right. And your book goes into the wind speed is increasing with height, and we need to understand that. We need to understand how wind velocity varies with height above the surface in planning towers. And so the book goes into this thing called the log law wind speed profile. So the log law wind speed profile assumes the shear stress in the wind is constant with height up to about 100 to 200 meters, which they call the surface layer, or we could call the atmospheric boundary layer. We've talked about that. So for a smooth surface, the mixing length L of the turbulent wind is equal to some constant. That's von Karman's constant. I don't know the derivation of this. I'm not familiar with this, but that was developed, for aerodynamics. And Z is the height of the ground. So basically, the mixing length increases with height. So here is a log law wind speed profile for the surface layer. So here we're looking at height, and here we're looking at a velocity of, it's basically reaching a maximum somewhere up here. It's sort of asymptotically approaching that, maximum wind speed. And you can see that the wind speed is lower near the surface and higher with elevation. So there's two unknowns in this equation, right? This velocity equals the friction velocity from the shear stress divided by von Karman's constant divided by times the natural logarithm of the height of the tower versus the surface roughness length. So there's different kinds of surfaces and they have different kinds of roughness lengths. So cities and forests have the largest, and flat deserts and the ocean have the lowest, right? So that means that the shape of this profile will not change, but how long it takes to asymptotically reach the maximum velocity will change, and we'll see an example of that. So here we've got a rough surface like a city, and over here we've got open land like the high plains. So what you can see is, it's in both cases, the wind speed is 0 at the surface, and then it slowly increases 30%, 51, 61, 75, 90, 94%. It reaches basically 100% of the free slip velocity at 500 meters above a city, a rough surface like a city. Whereas out in the open land, it reaches that, where there's much less surface stuff to cause turbulence. It reaches that at more like 250 meters, half the elevation. So, forget about how ridiculous it is to try and put a wind turbine in a city. This open land, rangeland, has got the lowest surface roughness. So you reach that maximum velocity at a lower elevation above the ground, a lower height above the ground than you would in the city. So another reason to go out and put these towers out on the ranges. All right, so wind tower height matters a lot to the wind energy, given that. So recall that the power increases as the cube of the wind velocity, right? We've seen this equation before, very important one. And what you can see is, here we've got an example where the wind speed increases 18% from 7.2 meters per second at 40 meters above height to 8.5 meters at 95 meters above the ground. So that is, we can plug in these numbers, and by going from 40-meter tower to a 95-meter tower, you're getting 64% greater power. I mean, this is simple economics. That's what's driving these tower heights, at least on land. So another consideration is atmospheric stability. And your book talks about the three stability states of the atmosphere. But in here we're seeing, there's three. There's neutral, there's stable, and there's unstable. So here's neutral, right? This cloud is not sinking or rising. Here we got sinking. This cloud is sinking, and here's one that's rising. So neutral occurs when there's no change in temperature with height in the surface layer, atmospheric boundary layer. And that only happens between episodes of stable and unstable. So stable environments occur when the air on the ground is cold and warmer above. So in that situation, cold air is denser than warm air, so it's not going to rise. It's going to basically stay that way. So that's generally associated with high wind speeds aloft and steep increases in wind speed with height in the atmospheric boundary layer. Unstable is when the air near the surface is warmer than the air above it. So rising air causes turbulence that decreases wind speed gradients. Okay, so now think about Texas wind energy up in the plains. When would there be stable conditions and when would there be unstable conditions? Anybody have an idea?
Summer is unstable and winter is stable.
Yes. So that's exactly right. And this is one of the problems with wind energy for Texas. Our electricity demand, doubles from winter to summer. So, yes, it's something to keep in mind. All right. So why is the stability state of the atmosphere important for wind power generation? And the answer is this affects the flow conditions of the atmospheric boundary layer and is relevant for both onshore and offshore wind energy sites. Now think about offshore wind. Is the atmospheric stability offshore better than the atmospheric stability onshore? What does anybody think?
Yes.
Yeah, it doesn't. You rarely have the condition in the summertime where the ocean is warmer than the land, so it's going to be relatively stable compared to the land. So you can see some advantages in thinking about offshore wind turbines. Now, it doesn't really help Texas because Texas, the wind near shore in the Gulf of Mexico is not that strong. So, the wind resource is definitely on land in Texas, but there's other places where the wind resource is offshore. What's happening? Here we got a wind farm, and the conditions were just right that the turbulence led to condensation in the zones of turbulence. And what you can see here is there's a wind tower, and down, this is the wake, right? The wake of the wind turbine. It's like a boat wake or an airplane wake. It's the disturbed air behind it. And you see this effect in contrails in the sky where the jet's not only causing turbulence, it's also injecting a lot of water into the atmosphere as part of the exhaust. But this is a nice image showing, visualizing turbulence, which normally we can't see, right? But when the turbulence results in cloud, condensation and clouds, you can see it pretty easily. So you can see that this wind turbine, its wake is interfering with this wind turbine, which is interfering with this one, and so on back the line. So, when you're doing wind energy, you have to pay attention to this. Otherwise, you're going to lose a lot of money. Your investors will. Okay. So let's get going from here. And don't hesitate to ask questions. So stable wind conditions, and when I say stable, I'm not talking about velocity, I'm just talking about the lack of turbulence. They imply longer and more pronounced wind turbine wakes. So unstable conditions can disrupt this. So there's the natural instability of the atmospheric boundary layer, and then there's the turbulence caused by the wakes themselves. All right. So these wakes affect both the energy yield and the loads of the wind turbines. So, affecting the load is basically causing, chattering. Everybody knows turbulence because when you get in the air, the plane goes up and down. That's what turbulence is doing to the airplane. But if you imagine a wind turbine, dealing with this turbulence, it's going to be shaking and that's going to lead to increased maintenance cost. So this thermal stratification is linked to wind farm planning and to calculating the annual energy production. So is that clear? Because if you have any questions, just raise your hand and we'll explore. Oh, yes, John.
Well, actually, this is a simple question, which I don't quite understand. Why is the condensation happening? I mean, it's got to be simple chemistry, but I mean, is the lower velocity cool it, or I'm not sure why you're even getting condensation behind the windmill.
And that's a good question. And I can't answer it. You'd think I could, but I can't. But condensate, obviously the conditions are just about right for condensation. There'd be fog here if it wasn't for some slight variable. But, turbulence stimulates nucleation, perhaps of water vapor into droplets. That's where clouds are, is little droplets of very, very small droplets. Yeah. If they get to be big droplets, they drop as rain, but small droplets will just make clouds.
So Stephen,
what's that?
Clint or Stephen, do you guys know why that happens?
No.
Okay.
Other than that, when things are just on the boundary of a phase change, just ready to do something, and then something else, you change something else in the system. Kind of like it's unrelated, but if you take a bottle of, Kroger Sprite and put it in the freezer for, until it's real cold, and then you take the lid off, it goes and it turns to ice. And you actually see the crystals growing down like this. It's interesting experiment. So this is kind of the same thing. It's like, the air was coming along, it wasn't going to change, and all of a sudden, and the phase changes from vapor to actual droplets.
Yeah, and there's some really cool videos. What these guys do is they take a plastic bottle of water and put it in the freezer, and they're very careful not to shake it. And then when they get it out, so it's well below freezing, but it's still liquid. And then they just tap it on the counter, and it freezes almost, turns to ice almost instantly. Something causes nucleation. So yeah. Good point. All right. So here the book starts talking about your power law wind speed profile. This is the power law, right? As opposed to the log law. So that's the velocity at a given height is equal to the velocity at a reference depth, reference height times the height over the reference height to this power alpha. So alpha is the shear component. And here you can see the models for the log law wind profile. Now, this is the log wind profile here that we just talked about. And there's power law with an alpha of 0.14, 0.17, 0.23, right? So the velocity at height, and remember, we're getting up into these heights. You know, which one of these laws is most appropriate for the region that's being considered as a wind farm is important. And your book talks about that for neutral flows, you know, we were talking about these, you know, atmospheric stability. So that right, unstable sinking, rising. So for neutral flows, alpha is about 0.143. For unstable flows, alpha is less than 0.1. And for stable flows, alpha is greater than 0.3. So you can see this alpha has a huge effect on the winds aloft. Like you'd much rather have that speed wind profile than this one, right? That's a huge difference. 14 meters per second versus 11. And you know what that means in terms of electricity production, right? The cube of the velocity. So you want a high alpha. So here are the calculated wind speeds for two different alphas at 100 meters, right? And remember our wind towers. Let's go back and look at our wind towers again. You know, 2016, they were, you know, the hub was at 128 meters. You know, now they're getting up to, you know, I don't think we're going to see any of these in Texas for a while, but, you know, Texas is somewhere in this range of 130 to 260. And it might be a fun project for somebody to look at sort of what is the typical hub height now for wind velocity in Texas? All right, so you're looking for something that's going to give an alpha. That should be an alpha, you know, this high as possible. You can see the difference in the wind speed for those two alphas. So there's a 89% greater with a higher alpha. So, you know, getting this right is critical for any kind of you know, budgetary analysis, projections about what's going to happen financially to the company. Very important. So then the book goes into this probability of observing a given wind speed. So here we're looking at a Gaussian PDF, right? So what you've got here is the frequency of events versus the magnitude of the event. This could be anything. This could be earthquakes, oil fields, you name it. Grades, well, maybe not grades, I don't know. But this is a Gaussian distribution. This is simple statistics. So that's a normal probability density function, right? Here's the mean of all the values. And this area relative to this entire area is the probability of some velocity of some thing happening at this interval. So you need to understand the probability of observing a given wind speed at the elevation you're interested in, right? So you're going, okay, that's pretty easy. But the reality is wind does not follow a Gaussian distribution. So here are the probability density functions. I agree, it's confusing. PDFs usually means something else to us than probability density functions, but this is a probability density function for wind velocities at, in general, they're not Gaussian. They're generally skewed to lower velocities. So obviously, you know, here we've got, you know, a Rayleigh wind distributions going from 0 to 30 meters per second. and the relative probability. So this one would give you a 4 meter per second annual mean wind velocity, wind speed. This one would give you 6, 8, 10, 12, right? So you really want to have that understood. And you have to measure it at some, figure out what it is at the elevation above the surface that you're interested in. So now wind turbines can't operate unless if there's no wind. That goes without saying, but they also can't operate if the wind isn't high enough. So one of the things that a company wants to know is what percentage of the year will the wind velocity be too low for a wind turbine to operate? And this is the cumulative distribution function. So now the book takes this stuff and starts talking about turbine performance. So it builds on section 8.5 to understand blade aerodynamics. So we're going to see that there's some engineering tricks you can do to deal with this. It'll help deal with some of these problems. But basically, this is a very simple diagram. Here's the power, that the wind turbine is going to put out. And here is the wind speed. And it's very important to understand the cut-in wind speed, which is when the turbine starts rotating and starts generating power. This is the rated wind speed. This is the speed at which the turbine is getting the maximum. And this is the cut-out wind speed. So you basically have to shut down your turbine when the wind is too high. So this is something, a lot of people don't appreciate. And then what we're seeing here is the power in the wind. Anybody have an idea why this curve doesn't follow that? Can we get a hand? I think we talked about it.
Beck, or I can't remember what 4-letter name.
Yes, the Betz limit. Yes, that's 59%. This turbine power is 59% of the wind speed, right? Good. Betz. It's almost like Mercedes-Benz, but not quite. So obviously he was German. All right. So basically you've got 3 sort of intervals for a turbine. There's no power generation until the cut-in wind speed is reached, right? Which is like a few meters per second. I don't know. There's the cut-out wind speed when the wind turbine is turned off because it's just the money it might generate is not worth the additional maintenance cost or replacement costs. And then this is the rated wind speed, is the wind speed, and actually the wind speed interval at which the turbine is operating near its peak efficiency. And obviously, the goal is to operate the wind turbine near its maximum efficiency as much as possible. So when we talk about wind power capacity, this is what's being considered. But the reality is, with the wind velocity probability density functions, it's not going to be that speed all the year, even in the high plains. Let's watch a video.
Now, a real wind turbine, if you look at it, it's going to take a bit of a wind speed started. You with that? So there is a region from 0 wind up to a certain wind speed called the cut-in wind speed, where there's no power produced by the wind turbine. Also called the region 1. Nothing's happening. Then, once the cut-in wind speed is reached, power ramps up, and you can see that it's in an almost parallel slope to the power that becomes available with the wind speed itself, but it's only a certain fraction of that amount that actually a machine, the wind turbine rotor, can capture. And we're going to learn about how much that is. That region called region 2. Power ramps up. So ideally, want to produce power with wind turbines, want to make money, right? Want to sell the power. Ideally, you want to go all the way up here, but you're limited. What limits you? Generator. Okay, first thing that limits you is the generator. Generator can only take so much power and feed it into the electrical grid. So you have to start controlling the power. That's the typical power curve of a modern pitch-controlled horizontal axis wind turbine. So you control the power by changing the blade pitch, changing the loads, and hence the torque and power produced of the rotor. So that wind speed, where you reach the rated power of the turbine and the generator, it's called the rated wind speed. And from there on, as the wind speed increases, we're going to see you have to pitch more and more the blades to accommodate for the fact that more wind power is coming in, but you are only allowed to capture so much of that. So essentially, you have to adjust the blade pitch angle such that local angles of attack acting on local airfoil sections become smaller, hence the loads become relatively smaller, and the power stays the same. So then back at the end here, usually if the wind speed becomes about 25 meters, you have to shut down the turbine. Why is that? Not a generator problem. Becomes a blade loads, becomes a load and fatigue issue. So if it's a storm condition, also in the storm, you have more fluctuations, large amplitude, and that poses a problem. You have to shut down the rotor. So that's the cutout wind speed. So we're having these three distinct regions in the power curve of a modern pitch-controlled horizontal axis wind turbine.
Now, we haven't talked about pitch control yet, but we will. Disk theory. So we talked about the Betz limit and why there has to be some velocity in the air behind the rotor, but it's going to be a fraction of that coming in. So here we're looking at a very simple equation. The velocity of the wind is greater than the velocity of the disk. The air through the disk is going to be greater than the velocity of the air through the wake. So the mass of the air moving from left to right is constant, and because the velocity decreases behind the rotor, the area of moving air must increase. So the book talks about the axial induction factor, which is just the velocity of the wind minus the velocity of the disk divided by the velocity of the wind. That varies from 0 to 1. A low A means a slow wind, and the upper limit on A is the Betz limit. Then the velocity of the wind through the disk is 1 minus A times the velocity of the wind. And then you can use Bernoulli's theorem to calculate the velocity of the wind behind the rotor and see how wide this region of wind velocity is going to be. Now, this wind is coming in at this velocity everywhere, but right here there's going to be fast wind interacting with slower wind, and that's going to cause shearing and turbulence in here. That's what's going on. There's a lot of reasons there's turbulence behind a wind rotor. One of them is the rotor itself rotating is interjecting some disturbances, but in addition, there's shear along this velocity profile. So the book continues discussing these things and uses this information to calculate the coefficient of performance, which is the power in the wind, the power of the aerodynamics, the wind in the turbine divided by the power in the wind, So here's the coefficient of performance going from 0 to 1. And this is the axial induction factor. And the book says that's the maximum power is set by the Betz limit, occurs at A is equal to 0.3, or about 0.33, right about there. And the maximum thrust is there. So anyway, the book goes into that. That won't be on your test, so don't worry about that too much. So this is, your book shows this. This is a flow visualization test using a NASA wind tunnel using, so this, what they're doing is they're making this rotor and they're emitting smoke from the tips of the turbine, and that's helping researchers understand this vorticity turbulence that the rotor is imposing. Okay, and then the book goes on to talk more about actuator disk theory. And they point out that in practice, the power coefficient is a function of many variables, including wind speed, blade pitch, angle, and the tip speed ratio. And basically, they talk about the coefficient of performance and then rearrange to calculate the power extracted by the wind turbine. So this, given a coefficient of performance and the probability of wind speeds, then the annual energy production can be estimated, and this allows levelized cost of energy to be determined, which is the backbone of all of these evaluations. Any question about that? All right, so here we're looking at an example from your book to determine the annual energy production for a wind turbine with certain characteristics A. So here's the power, and we went through this equation. So obviously, the wind velocity is the thing that you want to understand, because your coefficient of performance is set by the engineering. So they're giving an example. First, calculate the power at 10 meters per second, which is shown there. And that's equal to 0.5 times this, all of this, and that gives you 2,000 kilowatts or so for that wind speed. So you can see that wind speeds between the rated wind power and the cutout speed, so that is constant at 5,000 kilowatts. So you really want to know how many days of the year is the wind going to be at this speed at the height of the rotor, and then also you're going to get some power out of this part as well. So that's the rated power. So and you'll see that when people talk about how much wind energy capacity there is in Texas, they're dealing with the rated wind power times the number of turbines. So limiting power production to rated power is needed for structural stability and to limit electricity added to the grid. We haven't even talked about what ERCOT's going to tell these companies about how much of their energy they want. So the next thing you do is use a probability density function and calculate the power for all likely wind speeds. So we did one, we showed how to do it for this interval at 10 meters per second. And so you just do it like that. Here we've got the number of hours, wind hours per year versus the wind speed. You can see here the median is between 5 and 6 kilometers per second, but then tailing off like that. You have to calculate the power for all likely wind speeds. So here's it from your book, from wind speeds going from 1 to 25 meters per second, which is obviously the cut out wind speed. No, it's not. It's actually, there's no wind speeds over that. But apparently this is below the cutout wind speed, which is interesting. But basically, there's a probability from the probability density function, number of hours per year, multiply this times that, and that gives you the kilowatts. That gives you the total that you can expect, and that can be multiplied by the price of electricity that the company is selling to the grid to calculate, okay, that's how much money we're going to make, or we should make. All right. So the capacity factor of wind turbine is a ratio of energy produced to the rated power times hours per year. So in this example, it was 13,000, right? Megawatt hours. It's 13 megawatt hours, right? Isn't that right? So, no, I got that wrong. Yeah, that is, oh no, there's 1,000 megawatts in a kilowatt. That's what we're doing. So it is 13,873 or 880 megawatt hours. And the rated is 5 megawatts for this thing, and there are 8760 hours in a year. So this is what it could generate if the wind always blew at the rated wind energy, you know, between the if the wind always blew at that velocity. That's what this number is. So if you look at that and you divide it by this, you'll get 31.7%. And the book is telling you that your typical wind turbine capacity factors vary between 20 and 40%. Obviously, you want to be at 40%, not 20%, because it's not going to cost that much different to put up a wind tower. But if you have that big of a difference in the amount of income you're getting, that's going to be an issue. All right. Now, we haven't talked about blade pitch. Let's watch this video and learn something about it. Uh-oh, got to go back at the beginning. Sorry about that. So what you're seeing is the velocity, the rotating of the turbine. And if you look on the right, you'll see what's happening to the blade pitch. It's changing as the wind velocity. The wind velocity is not changing, but you can see that the turbine is rotating more slowly as you increase the pitch. You know, as you get it to that, it's basically stopped. And that's a thing that you can do to deal with, you know, variable winds. You know, just adjust the blade pitch, and that's done automatically by computer. Okay. Now, obviously, there's a lot of engineering going into this. You know, because very small improvements will result in significant cash flow differences. All right. And your book talks about what that does to the power curve. So there are two examples being shown here. One is the rotor speed held constant by varying the blade pitch. So that's constant speed, variable pitch control. And that is the solid line, right? Which, reaches the rated wind power at a slightly higher velocity than this other one, where you basically can vary both the rotor speed and the blade pitch. So that's variable speed and variable pitch control. And look, you can get the cut in velocity much lower. And even as you approach the rated power, you get additional energy. So you can, you can replace this area here with dollars, and lots of them. And what your book talks about energy production and capacity factors for variable speed, variable pitch, and constant speed, constant pitch. So the energy, being generated varies by, what is that? 1,800 megawatt hours. The capacity factor goes from 27.5% to 31.7%. Okay. So you get a much better total output with variable speed, variable pitch, about 15% higher for the same wind conditions. So it'd be interesting. You imagine that all of the new ones going up are going to have this, but our next lecture is actually going to be a talk by a professor in mechanical engineering whose specialty is wind energy, and he may show some of these stuff. I don't know exactly what he's going to show. I've asked him to talk about UTD's research in wind energy, and so I'm not sure what he's going to do. All right. So then the book goes into levelized cost of energy for a wind turbine, and NREL, which of course now is the National Rocky Laboratory, because renewable energy is a dirty word now. So this tool focuses on the most widely used technologies, which are horizontal axis wind turbines, 3 blades, upwind, pitch controlled with variable speed, both for offshore and onshore. And there's a tool there that you can dig into if you're interested. So the levelized cost of a single wind turbine, right, is given here. The levelized cost of energy is equal to the fixed interest rate charge times the initial capital costs divided by the net annual energy production plus the annual operating expenses, right? That's very simple levelized cost of energy. Now it's like, what is the annual operating expense for a wind turbine? So that is shown here. The annual operating expense for a wind time is the land lease cost, the dollars per kilowatt hour. It's basically like an agreement with any landowner if they were drilling for oil, and they get oil out of somebody's land, that the landowner gets a fraction of that. I guess that's how it works. Is it, Clint? And do I have it right?
Hang on, sorry, what?
Let's imagine you've got an oil well
Yes,
that's
you do.
producing.
You get a 25% royalty in Texas.
Okay, I don't know what the royalty is for wind energy, but I can't imagine it would be a whole lot different. I mean, wind is like oil, only it's renewable.
I imagine not, and I should point out that your cows do a lot better. You make a lot more money ranching when your cows can rest in the shade of either a pump jack or a windmill.
So it's a win-win. Okay, so there is this land lease cost, and then there's levelized operation and maintenance. You've got to have a budget for going out and making sure everything's working right. And then there is a levelized replacement or overhaul costs, because these things don't last forever. You've got to amortize what it costs to replace it. So those things go into the annual operating expenses in there. All right, so the initial capital cost for a turbine system is the turbine system itself and what they call the balance of station costs. So the turbine system consists of the rotor, right? Then the drivetrain. We talked about the gearbox, because these things rotate pretty slowly, and then that's geared up to get to the rotations that you need to generate electricity. We're looking down on it, so the tower's underneath here. And then there's the inverters and all of the electronics you need to turn that into the electricity needed for the grid. And it's all housed in what's called the nacelle. And that total, that is a very significant cost. And then the balance of station is basically foundation, support structure, transportation. You might have to build roads. There's assembly and installation, electrical interface connections, cables, engineering permits. So this is typically $700,000 per turbine for onshore. So your book gives the example of a typical onshore turbine, which costs about $1,100 per kilowatt. So a 5 megawatt turbine, which isn't a ridiculous, and that 5 megawatt is the rated power, right? As we just discussed. So that would cost $5.5 million, and about 700,000 of that would be the balance of station costs. And then offshore turbines have additional costs because you have to modify equipment for the marine environment. You've got port and staging equipment. You've got personal access equipment. People have to be able to get on the turbine and service it. Scour protection around the base of it. There's got to be a surety bond, which covers the decommissioning because these things sometimes come down. And then the offshore warranty premium. So this is sort of the typical operations and maintenance cost for a typical wind turbine. So this is for a megawatt scale, the drivetrain, the balance of station costs, operations and maintenance, levelized replacement costs, the rotor, the tower, the controls. So that's just sort of where the different costs go for the operations and maintenance costs. All right. Yes, John.
Well, not to be controversial, but I think this kind of understates the cost, and that's been one of the issues historically is you're taking the cost of putting it in place, but these are usually especially the offshore ones are very far away. So you got to put in a huge amount of infrastructure, expensive infrastructure to move it to the cities from West Texas or move it offshore into the cities and things like that too.
Oh, absolutely. No, there's no question that an offshore installation is more expensive than an onshore for the reasons that you say. But the book goes through an example of the levelized cost of energy example for an onshore. I believe this is onshore, turbine ratings, capacity factor, turbine costs, operations and management, fixed charge, the rest of station, levelized replacement costs, land lease costs, for some reason, $0 a year. You work out the energy production, go through these equations, and come up with numbers that tell you, oh, we're going to make money, oh, we're going to lose money. So, then the book talks about, do windmills pay for themselves? Windmills, wind turbines. The following example is very simplified, but it demonstrates the concept. So according to the U.S. Energy Information Agency, the average wholesale price of wind power in Texas is $26 per megawatt hour. So that's equal to 2.6 cents per kilowatt hour, significantly less than what we're paying. And that's likely to go up because we're going to need more electricity in the future. So assuming a 3 megawatt wind turbine, the installed cost ranges, the book says, from 2.3 to 2.5 million. And remember, this book is a little bit out of date. At 45% capacity factor, turbine generates that much electricity, and it generates that much money. And then if there's a tax credit, that changes it. There were tax credits. I think those are going away now. So then looking at operation and maintenance costs, they're looking at 150,000. So it generates a cash flow of $250,000 a year. So, these numbers it would be very interesting to know what the real numbers are now in Texas, but that's a pretty significant return on investment. And it's in a nutshell, is telling you why the conservative businessmen of Texas are investing massively in this wind energy. So if you look at the payback period, in this example, it's 7 or 8 years, and a wind turbine is expected to last 30 years. So after 7 or 8 years, you have got a nice cash cow. All right. Then your book goes into wind farms. We've been just talking about individual towers, and wind farms are what's actually happening. So at wind farms, they're not growing wind. They're basically groups of turbines producing electricity at a single location, right? It's just a lot simpler to have them grouped together as much as possible, in terms of infrastructure, in terms of operations and maintenance, in terms of organizing the land. What I found is that right now there are about 150 wind farms in Texas, which have a total capacity, right, of over 30,000 megawatts. If we multiply that by, say, a 30% capacity factor, it's generating on the order of 10,000 megawatts per day, 10,000 megawatts on an average day. And that's equivalent to 12 Comanche Peaks, which is the way I like to think about energy. That's a lot of energy because Comanche Peak, one of the two nuclear plants, is generating on the order of 10%. The two nuclear plants are generating on the order of 10% of Texas electricity. So Comanche Peak's 5%. So you can see where they are, right? Here we are on the high plains. They really like this area around Abilene. And then there's some in South Texas too. So, the sweet spots are pretty well identified. And those are the top 10 Texas wind farms by capacity in 2023. Roscoe's the big boy there. Huh? So I found that there's 239 wind-related projects in Texas and more than 15,000 wind turbines, which is by far the most of any state. And you don't hear much of the state government is slightly concerned, but they're basically concerned about the fact that this is an intermittent energy source. And so we need, as we ramp up electricity demand, we can't just ramp up these intermittent sources. We need to have base power generators like natural gas or nuclear or something like that. And that's kind of what's going on in the legislature these days. All right. So then your book gets into some more details about wind farms. So your book says capital costs on the order of $1 million per installed kilowatt. These need to be near transmission lines, right? So you're not going to put up a wind farm if there's no transmission lines nearby. On the other hand, if ERCOT and the grid builders are putting in a new line, you're going to want to know if it's going through the area of interest. So once you've got that sorted out, then the question is, what's the best way to arrange these wind turbines? You've got a prevailing wind direction. It's not going to always come from exactly that direction. And so, if it's coming from this direction, that turbine is going to interfere with that turbine. So you can see what's going on here. They're basically saying, okay, the downwind spacing with respect to the prevailing wind direction will be that many meters or whatever. So the question is, how do you arrange these in a grid that's staggered by a specific number of rotor diameters? That's how they think about the spacing, is the rotor diameter. So how many rotor diameters do you need to space so that this wake doesn't interfere with this? And that's, as we alluded to, these wake effects cause problems for downwind wind turbines. So here's a video talking about the wake effect. So you'll be seeing this, what's going on with power for a couple of turbines, one interfering with the other. And you can see that this is high power and then it drops off. This is kind of a numerical model for what's going on with the wind. And this is sort of a profile with one wind turbine here and another one down here. Yes, Clint.
And then there's the Irish wake effect. Okay, I'll shut up.
Oops, sorry. There we go. So this goes on for quite a while, but this is just basically setting up the experiment. We don't really need to watch that. I think they're going to leave it up for a while.
You should be able to click ahead. Maybe.
Yeah. Now you've gone and done it. So here we got two turbines operating in line. So there you can see where the two are, and you see the wakes coming back from them. So there's the power being generated in the second one as a result of the interference from the wake of the first one. That color scale is telling you something about the wind velocity relative to the incoming wind velocity. So you don't want that because that second turbine is not producing maximum power. So here we've got an offset, and it's only a partial offset, but you can see that the energy, it's quite variable. There's a lot of turbulence. That's why the wind, the power coming out of the second one is varying so much. So you want to avoid this. You want to plan your wind farm so that this problem is not significant. Right? There we go. All right, so here we're looking down on a wind farm. You know, those black dots are the turbines. And then we're looking at the velocity. So it looks like the wind coming in is on the order of 12 meters per second or so, 11 or 12. And then what you see in these, right behind each turbine, it drops way down and then it recovers. So what you would like to do is, as much of the time as possible, to have this wake not interfere with a turbine behind it. Now, this is done by Doppler shortwave radar. So this is done at Texas Tech, where obviously they're way out there by the wind energy corridor. But this is the sort of thing that we're going to hear about on Monday, and you know how researchers in this field actually study this in real life. So here we got wind power ratio for, this is the first turbine, and here's the second turbine. So this is the wind power ratio. Local wind power normalized by wind power level at an inlet. And so we're simulating what's going on. So you have to do numerical modeling to model these various configurations of turbines on a wind farm to extract maximum energy. And you'll hear about numerical modeling in a lot of geosciences related studies, you know, basically using computers and appropriate physical models to model the behavior of what's going on. So here's an example. Here's a wind turbine and what's happening behind it. And this is basically the wind turbine. And that's D naught, diameter of the wind turbine rotor. This is the incoming wind velocity profile. This is sort of taking into account this change in wind velocity as a function of height above the surface layer, right? So you can assume that. And then this is the distance downwind as a function of rotor blades. So X divided by D naught. So this is 4 rotor blade diameters down. This is 8, this is 12, this is 16, this is 20. So obviously you want a big rotor because you get more power out of the wind if you have that. But the bigger it is, the more it's going to cause problems downstream. So this is the model prediction up here, and this is what's actually measured using the Doppler. And you can see it's pretty good. So this is a video from the UTD wind turbine, which is just up the hill at the that research center that I forget what it's called. Anyway, just up on Waterview, just up the hill. So this is a wind tunnel where you can do experiments. Oh, it's Waterview Technology Science Center, just at the top of the hill, up Waterview. So here they are building it. All right. So that's kind of a cool thing a lot of people don't know about our wind tunnel. And they were having some problems with it. I'll be interested to hear what Valerio says about it on Monday, whether it's a back up and running or what's going on. Now, let's talk about offshore wind energy. Now, let's compare these two maps. They're both showing wind velocities using the same scale. And what you can see immediately is that offshore wind energy is higher than onshore wind energy. Now, and it's interesting where it is. So the offshore wind energy is really high off of Northern California, Southern Oregon, not very high off of Texas. So we don't really expect to see a lot of offshore wind energy in Texas. But look at the resource over here off of New England. And the other interesting thing about this is that this part of the United States doesn't have very good onshore wind energy resources, but it's got a huge offshore wind energy resources. So the United States has been looking at these offshore wind energy resources, especially for the Northeast. Right? Look at this. You know, there's this dark red. You know, I don't see any brown, but it's the orange and red. It's typically, you know, on the order of 10 meters per second. That's a really nice wind resource. So let's go compare that to our Texas wind resource. Yeah, we're in this kind of purple region, which is on the order of 8.5 to 9 meters per second. You know, so there's this offshore wind resource is actually better than that in Texas, but you know, as John suggested, there's a lot of other expenses associated with offshore wind, just like there is with offshore drilling. You know, there's some tremendous opportunities there, but it's a lot more expensive than onshore drilling. So let's see, 10 meters per second. That would be a superb wind resource, according to this. Now, this is U.S. Offshore wind power development, which is being developed basically in this corridor. And you can see the size of these energy. There's really nothing going on off of Northern California to speak of, but offshore the East Coast, tremendous. So these are the targets. Certainly there's a lot of opportunity in California, but even little Rhode Island, you know, Maine, Connecticut, Maryland, places where they have no onshore wind, or as we'll see, solar resources, they have huge offshore wind resources. Yes, Clint.
Right. And even though I haven't been there, and I don't know if any of you guys have, but you've probably all heard of nor'easters, and they are a thing.
Yeah, and they're almost certainly, they'd have to shut down the towers because that almost certainly would exceed you want that steady wind, the strong, steady wind that they get there.
Well, my guess is they have plenty of that too. Otherwise, there wouldn't be any planning towards it.
Yeah, they're not going after northeasters, that's for sure. So the offshore wind farm advantages, especially for the Northeast, they do not occupy land. So this is a huge advantage in high population areas like coastal, New England, New York. They have better wind resources. There's reduced turbulence, right? Because the ocean doesn't have the roughness that the land has. There's steadier winds offshore. They're higher winds, higher speed winds. So with that higher capacity, you've got a better match with the grid. It's a less intermittent source than onshore wind. There's this closer proximity to electrical load centers, so you've got lower transmission costs, better able to serve the high cost regions, and importantly, it avoids the land-based size limits. So you can use shipping, so there's no roadway limits. The assembly, you can use sea-based cranes, which can be taller, and these larger wind turbines are more economical. And there are significant problems in water deeper than 30 meters, but they can be, if the economics are such, it'll be done. The balance of system costs are double offshore wind farms compared to onshore. Yes, Clint. Yes, Clint. You got your hand up?
Sorry. Although it's there's problems with undersea cables of their own. Undersea cables is something we know about and do. And so that means you don't have to, for example, build towers.
Yeah.
Which is, so it's going to be expensive to get the power to the shore, but I don't know, maybe even less expensive than building, $1 million a mile towers.
Yes, I think it will be, but yeah, these things are just have to be aware of them. So offshore wind energy is modest now, but it's expected to increase tenfold by 2030. You can see what's expected for Asia, for Europe, for North America, Latin America, and the Caribbean, not much, and not much in Oceania, and Africa doesn't even sit on here. So that's the projection by the book, but the reality is that once again, the Trump administration has said that this is bad, and they've actually pulled permission for some wind farm developments, I believe off of Connecticut or Massachusetts, that are well underway, and just basically told them to stop, which is they're in the courts now. So it'll be interesting to see how that plays out. So, just to keep in mind, of the 48 contiguous states, 28 of them have a coast, and these use 75% of U.S. electricity. The New England states and the Great Lakes states have negligible onshore wind resources, but excellent offshore wind. And there's just a tremendous resource in here. And most, plenty of it lies less than 3 miles offshore in U.S. Waters. So your book talks about the gross resource potential for the different regions. The gross, which doesn't really much matter, but because the technical is always going to be a smaller proportion of that. But you can see that the North Atlantic is an excellent resource. The Gulf of Mexico maybe, but not so much in Texas. Anyway. So these support structures are interesting. Here's one that's actually just a post in the seafloor that's shallower, and it's possible to put moored buoys out there to support a tower. That's an interesting engineering feat. You know, these are going to be the most useful if you're in shallow water, less than 60 meters deep, but you can have them in deeper water if they're somehow anchored or floating somehow. So then your book talks about system advisory models for wind farm analysis. So it's a numerical performance and economic model. You know, people that are really want to get into this can look at this. And this one said that the NREL SAM is updated frequently. I'm not sure if that's true anymore because of all of the changes that have gone over the National Rocky Lab. And we're very well aware that one of the administration's biggest bugaboos is wind energy. We won't see as much criticism by the administration of solar photovoltaics for some reason, but wind energy, I wouldn't surprise me if this has all been shut down. And your book continues to do this, so you can look at that if you want. And that is the presentation. So I think we've really covered a lot of material today and the last time, and we're going to have a very interesting follow-up with a UTD professor next Monday. I hope you guys come with good questions. Ask him, because it's always hard for somebody who's doing research in an area to know how to pitch their talk. And I think you guys know an awful lot about wind energy now, and I hope you guys pepper him with good questions. So we're a little bit ahead, got a few minutes left. Is anybody got any questions or anything you want to discuss? Remember your project proposal is due a week from today during the midterm. So don't forget to send that in. If not, you guys have a good weekend, and we'll see you Monday.
Thank you.
Thanks.
You too.
Okay, bye-bye.
Thank you.
Hey, Bob,
Oh, hi.
you gonna be around at 3 o'clock Pacific time today?
I could be.
Okay. Tonight's my go to bed early tonight, but I don't have anything to do at 3 Pacific, 5 Central. So if you want to get together and we haven't looked at a manuscript 3 for 2-3 weeks.
What about 5 o'clock Pacific? Is that past
Nope,
your bedtime?
I'll be in bed.
Really? Okay. What about tomorrow
Yeah, tomorrow's good.
okay, maybe tomorrow will be better.
Let's see. Yeah, tomorrow about 3 o'clock Pacific time, something like that. Be okay.
What about 4 o'clock?
Yeah.
Because I'm hoping to get in the pool tomorrow. I got in the pool.
Oh yeah, no.
I got
Definitely.
in the pool I got in the pool Sunday and yesterday, so I'm hoping to get in the pool tomorrow.
Definitely.
Okay, let's aim for that. So
Okay. Will do.
yeah.
So look forward to it.
All right.
And but by the way, I've been posting my ads on various Reddit places, and it's gotten over 1,000 views, 1,300 views or so on the UT Dallas Reddit. Now, whether this is for the
Did you say
asynchronous-
1,300?
About 1,300 views. Now, views
From
means
UTD.
yeah, but this is Reddit, and there's a Reddit for UTD, and views doesn't mean anybody's watched the videos or taken the thing, but at least they're seeing it. So,
How many people have done the survey now?
I don't know. My guess might be 4.
Okay, well, we'll review it next time.
Yeah, we will.
Okay. Yeah, we'll see you tomorrow.
I will see you.
Okay, bye-bye.